Imagine a robot you didn't have to code. Imagine a robot that, rather than giving it the precise turns, angles, distances you need to get it from one end of an FLL board to the other, you could just tell it where you wanted it to go. You could just give it some waypoints and a final target.
Hello, I'm Colin from the Brickwolves, and today we're going to be talking about Pathfinder. Pathfinder is a piece of software we've developed to allow the robot to locate itself on the board. It uses the motor rotations as well as the gyro reading to accomplish this, and it actually works fairly precisely. It's a super cool piece of software, and so we wanted to show it to you. We don't have any code ready for a final release yet, as it isn't really compatible with various wheel sizes and motor configurations yet, but we've released a beta version that will be in the description, and you can track the progress of it on GitHub. So today we aren't actually going to be talking about the code, we're going to be talking about three things. The math behind it, because it's super cool math, also helps you to understand how this code works and how you might be able to even program your own version or better use our version. We're going to be talking about the story behind it, and we are going to be talking about what it is useful for. First up, how Pathfinder is meant to be used. The idea of it is that it can save you a lot of time coding something to get from one end of the board to the other. Instead, you just give it some waypoints so it doesn't hit anything, and you just tell it exactly the coordinate you want it to go to, and then what angle you want it to turn to once it gets there. This can save a lot of time on coding, because it can take forever to get just the right turns and stuff, whereas this software just does it automatically. The one problem with it is that it isn't super precise. So what you want to do is, once you get to the general area of the road, do something like line squaring, line following, backing up against a wall, or something else that's very accurate, so you regain a little bit of that, stud length accuracy that you need for doing a lot of missions in FLL. Before we talk more about the story of Pathfinder, I just wanted to talk about how we named it. Pathfinder is named after the Mars rover of the same name, and each version has a distinct name that's named after an explorer, adventurer, astronomer, or something like that. The current version, and actually has been the current version for a while, is Pathfinder Galileo, but other versions have included Pathfinder Shackleton, Pathfinder Copernicus, and we have a bunch more actually. The idea for Pathfinder began back in 2017 with the beginnings of our team. We noticed that navigation was going to be a big problem in FLL, and had started addressing this through MyBlock libraries that use things like gyro-corrected steering. By this season, we've built up a lot more MyBlocks that are even more accurate, and there might even be some videos on that coming in the future. However, these all require us to go in and manually code the robot and tell it where it needs to go on the board. The idea for Pathfinder really started in 2018, looking at inertial navigation systems in military aircraft. An inertial navigation system uses a 6-axis gyroscope, like the one that's actually going to be in Spike Prime, to locate itself relative to its starting coordinate. We had the idea to do the same with EV3 using motor rotations and the gyro reading. So in early 2019, we began developing this, although the first few prototypes weren't great. Through summer break of 2019, we developed our first few successful prototypes that could locate themselves on the board. In later 2019, we began working on something called A-star pathfinding. A-star pathfinding is an algorithm that allows the robot to pathfind itself around obstacles on the board, so that all we would have to do is give it a final target coordinate, and it could avoid things like mission models and other obstructions that might be on the FLL board. However, either due to the limited random access memory of the EV3 or some unknown error that we didn't find in troubleshooting, we couldn't get that working, and we put Pathfinder on hold for a while to actually start our FLL season. During our FLL season, however, an alumni of our school, who now works at NASA doing computer science and neural network engineering, talked to us about what we were doing with our robot, as he was there for a talk at the school. We asked him about what algorithms NASA actually uses on their rovers, and he said that he'd send a few papers along about an algorithm called D-Star Lite. We're hoping to implement this in kind of a Pathfinder 2.0 release that we'll put out at some point in the future, but for now we don't unfortunately have A-Star Pathfinding working. In January of 2020, we had the idea to, instead of using A-Star Pathfinding, simply give the robot some waypoints and a final target. After doing some troubleshooting and a lot of trigonometry to get this working, we got it working in late January of 2020. It's been a lot of work trying to get this done, so we're super excited to finally be showing it to you. Now on to the math behind Pathfinder. The way that Pathfinder actually figures out where the robot is on the board, and also the way it figures out where to go on the board given the certain coordinates, is through math called trigonometry. Trigonometry uses ratios in right triangles. A right triangle is, well, a triangle with a 90-degree angle in it, and the long side is called the hypotenuse, and these are sometimes called A, B, and C. Part of right triangles is Pythagorean theorem, which says that a squared plus b squared will equal c squared, where c is the hypotenuse or the longest side of the right triangle. There are also ratios between the angles and sides of the right triangle. The sine of an angle in the right triangle is the opposite over the hypotenuse. Now, what this actually means is that if you take a certain angle and ask a calculator for its sine, it will give you the ratio between the opposite and the hypotenuse. So let's call this angle theta, which is kind of just a word for kind of an angle variable like x is in algebra for certain numbers. The opposite of theta would be this side here, the adjacent of theta would be this side here, and the hypotenuse would be here. If the theta was here, then this would instead be the adjacent and this would be the opposite. But for now, we're just going to stick to imagining that we have a theta right here. So the sine of this theta angle would be the length of this side divided by the length of this side. The cosine is the adjacent over the hypotenuse, and the tangent is the opposite over the adjacent. So how does this help us figure out where the robot is on the board? Well, what we can do once we know these ratios is to say that we know the angle the robot has traveled at, and we know the distance that it has traveled. So we know the length of the hypotenuse, and we know this angle, theta. And we need to find these two distances here, x and y, which will basically be the x and y that the robot has traveled since we last knew of its position, or since its beginning position. So what the robot does internally in this software is it says, what is the sine of theta? Because you can get these from an advanced math block in EV3. And what is the cosine of theta? So we know the opposite over the hypotenuse, and we know the adjacent over the hypotenuse, and we know the hypotenuse. So if we take the sine of theta and then multiply it by the hypotenuse, which again we know because that's just the distance that the robot has traveled, we end up getting just the opposite, which is what we actually need to know. If we do this here too, we get just the adjacent. Now, if we know what actual quadrant of this is in, whether the robot has gone, negative x, negative y, positive x, positive y, but depending on which quadrant we know whether to add or subtract the opposite and the adjacent to either the x or the y, and so we can figure out where the robot is from its last known position. For this math to work though, we do need to know the angle in more of a standard 0, 90, 180 to 70. So if I just mark these out, this is a more standard kind of angle system than the one that the EV3 uses, where it's just either minus or plus and it just goes infinitely around. So the way we deal with that is math called modulo. If we take the input, the gyro angle, and we say mod 360, which looks like this in the software, then if it's 720, it will give us just 0, because 360 goes into the gyro into 720 twice with no remainder. That then can basically give us where we are on this. Now, to find the opposite, to figure out where we need to go based on our starting position, that's actually really easy, because it's basically just the opposite of that. We know the x and the y difference from where we are to where we need to be, and we just need to figure out this angle and this hypotenuse. So we know a and b, and we just need to figure out this. For the hypotenuse, we can actually just use Pythagorean theorem. A squared plus b squared square rooted will just equal c, because a squared plus b squared equals c squared, and if we just square root both sides, then we can get it as just a c. As for the angle, all we have to do is say that the b over a will be the tangent of the angle we're looking for, theta, and there's a function called atan, which will give us the angle from a tangent, rather than taking the angle and giving us a tangent. So the atan of b over a is going to just be equal to theta. And then we do the same operation with quadrants, and we figure out exactly the angle and the distance we need to steer. We then just use an incremental steering program and a very precise turn program to get exactly where we need to go. Thanks for watching this video. It's been a ton of work to get Pathfinder working, so like I said, we're super excited to finally be showing it off. We didn't do a super in-depth explanation of the math today, and we didn't really get into the code at all, but that's because we haven't yet actually finished our kind of final release of the code, which will be compatible with really any robot, and not just our specific StormX chassis. When we do release that code, we'll hopefully release a video going over the code more in depth and explaining precisely how all of the equations work so that you can better understand the software. Anyways, thanks for watching, and we'll see you in our next video.